We're going to propose now mechanisms and predict the products of carbonyl reactions. So I'm going to go in a very different order than your chapter goes, simply because I feel it'll make more sense to show you all the patterns between all the reactions rather than going in the order that they show it there. That's one of the things I hate about your textbook, is that it goes back and forth between different kinds of reactions instead of showing you all the commonality that underlies all of them. So either way, I'm going to cover the reactions that are within your chapter, just not in the order that they are presented in. I should also like to add that in your chapter, it first talks about how to synthesize ketones and aldehydes. In this review session specifically, I'm only going to focus on how to, the reactions of ketones and aldehydes, meaning what happens after they already formed, not how to form them. Because mostly we've already seen the synthesis reactions that give you a ketone or an aldehyde. You start with an alcohol, you treat it with an oxidizing agent such as chromic acid, or sodium dichromate, or PCC, and that'll oxidize your secondary alcohols to ketones and your primary alcohols to either aldehydes or carboxylic acids. So we're not going to go over those too much. We're instead going to go over the reactions of carbonyl groups. My point is that there are many, many nucleophiles that can attack a carbonyl group. Many, many nucleophiles. And that's because, as we mentioned, the carbonyl group is an awesome electrophile. So it can be attacked by many nucleophiles. In this chapter, there are 5 different classes of nucleophiles that will attack your carbonyl group. The first are what we call hydrogen nucleophiles, or what I'm calling hydrogen nucleophiles. What I mean is that the nucleophile that will attack will be a hydrogen atom. We're going to add a hydrogen atom to the carbon group. The second is oxygen nucleophiles, followed by sulfur nucleophiles, nitrogen nucleophiles, and then more carbon nucleophiles. So what we're going to do is we're going to start with our hydrogen nucleophiles. So the main source of a hydrogen nucleophile is going to be the reagent that we've already seen called sodium borohydride. I believe we saw sodium borohydride in chapter, I want to say it's chapter 11. I think it was chapter 11 or chapter 10. I can't. No, it was chapter 10. So it was on the structure of alcohols. And sodium borohydride, we remember, is a hydride reagent. It can donate hydride, not hydrogen atom, not proton, hydride, hydrogen with both of its electrons, to a carbonyl group. Let's refresh on the mechanism behind that reaction. So on the left-hand side, on the right-hand side, I have sodium borohydride. This is the Lewis structure of sodium borohydride. Observe that sodium is just counter ion here to balance the negative charge. It's not going to participate in the reaction. What's important is the borohydride portion of the structure. So boron, I don't know if you recall, boron is in the 3rd group on the periodic table, meaning it is trivalent. It only needs to form 3 single bonds in order to have a formal charge of 0. However, because of the octet rule, it can still make more bonds. It can make 1 more bond to have 8 valence electrons, but if it does, it'll have a negative formal charge. And that's what makes sodium borohydride a very good hydride donating agent. Sodium borohydride is going to want to eliminate its formal charge on the boron atom. And it'll do that by releasing the hydride. It'll release the hydrogen with its electrons as a hydride, and that'll take down the formal charge to 0 on the boron. So what will happen is that this hydride will attack our carbonyl group. After all, this is going to become H-. It's a nucleophile that can attack our electrophile, the carbonyl group. So that's exactly what just happened here. Notice the formal charge no longer exists on the boron. Let me show that again. because there we had two steps that I want you all to see. We had the attack by the hydride on the carbon. When we did that, we created a fifth bond to carbon. We cannot have 5 bonds to carbon. So what's going to happen is 2 of the electrons are going to move from the double bond onto the oxygen. So I hope you all saw that 2 things happened there. And we had our nucleophilic attack, and then we had our electrons move onto the oxygen. So now our oxygen bears that negative formal charge that the borane used to have. So now our borane is irrelevant. But now recall, students, I mentioned that after a carbonyl group is attacked, it will reform if possible. So this is a very unstable structure. What's going to want to occur is that these electrons are going to want to move back into the oxygen-carbon region, and they're going to want to form another carbonyl group like this. We notice, though, that that creates, once again, 5 bonds to oxygen. 1, 2, 3, 4, 5. We don't want that. So if this carbonyl group is to reform, one of these other substituents has to exit the substrate, because we can't have 5 bonds. So if it reforms, we can have maybe one of the alkyl groups leave, or we can have hydride leave. But let me tell you something, students. This will not happen. You will never expel hydride or a carbide ion. You won't expel those. There are some reactions, however, at the very end of your chapter where this does happen, where hydride leaves or carbon with its electrons leave. But this does not happen in this reaction, not with sodium borohydride. So this structure is going to stay intact the way it is. But I still have one more problem. I have a formal charge on that oxygen. We said we wanted to get rid of that formal charge, and we tried to reform the carbonyl group, but we saw that that's not going to work because we can't have hydride and we can't have a carbon exit. We don't do that. So instead, we have to find another way to get rid of that formal charge. And we do that via an acid-base proton transfer. So here on the right-hand side of the screen, I have put several acids. I have water, I have hydronium, H3O+, I have methanol, and I have ethanol. So students, all of these have a hydrogen atom that they can donate as a proton. In this case, I'm going to show water donating its hydrogen atom. So it donated its hydrogen atom without its electrons, so the electrons were left on the hydroxide ion that is still in solution. And that's how I got rid of my formal charge. I donated a proton, and now my oxygen has a formal charge of 0. So when we use sodium borohydride, students, we're going to donate a proton after the hydride attacks using either water or hydronium or an alcohol. It could be methanol or ethanol, whatever. We just have to donate a proton to get rid of that formal charge on the oxygen. Now we can also use another hydride reagent known as lithium aluminum hydride, which often is abbreviated as LAH, lithium aluminum hydride, and has the structural formula LiLH4. This one can also donate a hydride to a carbonyl group via the same kind of mechanism. You have your hydride attack, and then we have one of our proton sources, one of our acids, donate its proton to the alkoxide ion that forms and thus eliminates that formal charge on the oxygen atom. So you can use sodium borohydride or lithium aluminum hydride when you are attacking ketones and aldehydes, and you'll get the same product. So it doesn't matter which one they give you, just recognize that both of them accomplish the same thing, a hydrogen nucleophilic attack. So now let's go on. Well, are there any questions to this point before I give you the first question? Okay, since no one asked a question, then we're gonna do our first problem. Here I have question 1. Our first step is going to be to give the IUPAC name for this substrate. And then we're going to predict the major product in this following reaction. So I didn't put a timer this time, but I'll give you all 2 minutes. Okay, students, you have about 35 more seconds. Ten more seconds. Okay, so that's my timer. All right, first let's give the IUPAC name for this substrate. Who wants to offer an IUPAC name for the substrate on the left-hand side for our starting material? Andrea says cyclohexane carbaldehyde. Do y'all agree with Andrea? Okay, so I have about, I'm showing here, 20 students agreeing with Andrea, 4 students disagreeing, and 19 with no response. So of the disagreed, what would you say the name is instead of carbaldehyde? Instead of, sorry, cyclohexane carbaldehyde, as Andrea mentioned. I'll say that Andrea is actually correct. So allow me, it's not cyclohexanol. So remember, students, good guess though, if you have a ring structure and you have an aldehyde group, we indicated the presence of the aldehyde group if it's the highest functional group present with carbaldehyde. So that's the suffix. That's the suffix. That's what's important to remember. Carbaldehyde is not a name. It's just a suffix, just like Al. So this is cyclohexane carbaldehyde. And allow me to type that out instead because I don't want it to look messy. Cyclohexane carbaldehyde. It's all one word. It's not cyclohexane space carbaldehyde. Carbaldehyde is a suffix. So included as a suffix. Okay, very good, Andrea. So next we saw that we're reacting our cyclohexane carbaldehyde with sodium borohydride. And lastly, after that, we're applying methanol. So let's look at the mechanism for this reaction. I'm going to draw in the hydrogen on the aldehyde so we can see its presence. And we know that sodium borohydride is the source of the hydride ion, which I'm drawing in purple. The hydride ion is a nucleophile that will be donated to our electrophile, the carbonyl group. So it'll attack like this. And when that happens, that'll push the electrons from the double bond into the oxygen. So on the right-hand side, I'm going to get this structure. Then I have my hydrogen. That was my original hydrogen, and then my hydride that also added. So we see that we formed on this right-hand side an alkoxide. Do we want to have a negative formal charge on our main substrate? No. So what do we do to get rid of that formal charge? Do I just reform the whole carbonyl group? Methanol, says Aaliyah. Aaliyah, what do we do with methanol? What do we do with the methanol? What is the methanol for? Donate proton, says Skyla. Yes, the methanol will donate its proton. Perfect. So students, the MEOH, methanol, will donate its proton to our alkoxide. So specifically, we're talking about this H group. So our final product after the methanol is donated, the methanol acts as an acid that donates our group. We're going to have OH, and we recognize that that hydrogen came from our methanol. It was our acid. And then we have our hydride and our original hydrogen. So we see that in the end, we formed what kind of structure? We started with an aldehyde and we ended with an Andrea says alcohol. So does Roxana and Uriel. Yes, we ended with an alcohol. We actually ended with a primary alcohol, if we can recognize that. Oops, this should be a hydrogen. Primary alcohol. Very good. So we see that we synthesized a primary alcohol by the reaction of sodium borohydride with an aldehyde. If this had been a ketone, it would have formed a secondary alcohol. But this was a primary alcohol because we started with an aldehyde, not with a ketone. So this is a hydroxymethane cyclohexane, but I'm not going to have you give the name on the final structure. Aaliyah's asking, do we have to show the hydrogen that we first added to the structure, like the purple one? No. In fact, in the end, you can just leave your product like this. And that'll also be correct. We assume that the hydrogens are there if they're not shown. So in this case, I just showed you all so we can recognize that they still stay on there. So now, students, I'm going to give you this set of questions, and I'm going to allow you to write down these questions. So here are several organic structures that either contain a ketone or aldehyde or will lead to its synthesis. So what I'm asking you to do is select the one you want to select, and then try to synthesize the product. Hopefully you'll be able to. After that happens, you will tell me which one you want to solve, and I'll solve it for you. So I'll give you 2 minutes for this one. Pick the one you want to practice on, and then go. Okay, students up. So if you understand the mechanisms behind this hydride reaction that we discussed, you should be able to solve it, all of them pretty fairly quickly. But since I'll solve one for you, tell me, which one would you want me to solve? 1, 2, 3, or 4? So I put up a poll so you all can answer that. So majority of students I'm seeing already want me to answer number 4, which I will. Okay, so let's do number 4. Yeah, I know why I picked that one. So this is the starting substrate. Can we recognize what kind of structure this is? What kind of structure is this? Alkene. Very good. It's an alkene. Perfect. So an alkene, we know, is also a good substrate for the synthesis of ketones and aldehydes. We learned this all the way back in chapter 8. So I told you, please don't forget the reactions that you're learning in all the chapters because they'll come back to haunt you. So this one required you to remember a specific kind of reaction known as ozonolysis. So we had O3 in presence of DMS, and then we were also going to react it with lithium aluminum hydride, as well as, I believe, the acid was water. Okay, students. So we have ozonolysis, and we then have a hydride nucleophilic attack. So I hope you all recall that in ozonolysis, what we do, we use ozone O3 in the presence of dimethyl sulfone, which we learned last chapter was a thioether that is a good solvent for this reaction. So if we use dimethyl sulfide as a solvent and ozone, that is going to cleave this double bond in half. And it's going to add oxygen atoms, which I'll show, I guess, also in red, to both of the substituents on the right-hand side and on the left-hand side of the double bond. So I'll show the product. The product is still a double bond, but now the carbon is replaced by oxygen. And if I do the same thing with the other one, it's a symmetrical alkene, so it'll give me 2 symmetrical carbonyl groups. Now, students, since it's two symmetrical carbonyl groups, I'm going to have the same substrate. But sometimes if you use an unsymmetrical alkene, you'll get two different carbonyl groups. So in this case, can anyone tell me what's the name of this substrate? Either one, if they're the same substrate. What's the name? It's a ketone, but what's the IUPAC name of this ketone? But thank you, Skylar, for recognizing it as a ketone. So yes, ozonolysis is these two ketones. What is the name of this ketone? Dimethyl ketone. Okay, that's the common name. It's good that we're recognizing common names. What's the IUPAC name of the ketone? What's our strategy? Find the parent chain. How long is the parent chain? 1, 2, 3, right? Propane. So the parent is propane, and the ketone is at which carbon? 1, 2, 3. It's at carbon 2, says Jaden, and Jaden is correct. So this is propane 2 on. Perfect. So this is propane 1, and this is our substrate that we just synthesized via ozonolysis in the presence of dimethyl sulfide. Let's continue. We have lithium aluminum hydride in the presence of water. So this part should be a little easier now that we have discovered how to synthesize the ketone. So I'm going to redraw the ketone. And I have LAH. We know that LAH is going to donate it's lithium aluminum hydride. So what that hydride will do is it'll nucleophilically attack our carbonyl group, and that'll push the electrons onto the oxygen. Therefore, we'll get this. Andrea's asking, what did the DMS do? DMS is the solvent, dimethyl sulfide, that is necessary for ozonolysis. Oh, I should have done this one in purple. Okay, so this was the hydride that was added. I hope you can see that, students. Now, we added lithium aluminum hydride, and that made a hydride nucleophilically attack our carbonyl group. And lastly, we have that formal charge on the carbonyl group. So there we see that our last reagent, the water, is going to be our acid source that donates a proton. Oh, that was so ugly. That donates a proton to that carbonyl group. That's a little better. And gets rid of that formal charge. So that's what I'm going to demonstrate happens. We get an acid-base proton transfer. And our final product is this. So what kind of alcohol is this? We recognize that this is an alcohol. Secondary, yes, the secondary alcohol, and this time it's because we use ketone as a substrate. So if we wanted to be specific, this is propane 2-all. Perfect. Any other questions, students? Can I erase this then? It'll be in the recording, but that was our synthesis strategy. And I'm showing you all this. I know that I'm drawing it out. The reason I'm drawing it out, students, is because I really, really want you to practice with me drawing out your mechanisms. When I was grading your quizzes last week, I asked you all a question at the beginning if you were going to use a scratch sheet of paper. So you had 3 options. Yes, I showed my scratch sheet to the camera. B, no, I didn't, but I'll show it now. Or C, I will not use a scratch sheet. And we noticed that the students that they would not use the scratch sheet had lower grades than everyone else. So it's important that you have your scratch sheet of paper with you on your quiz on Wednesday. and on your exam on Friday, because you're going to be needing to draw out many mechanisms. And here I'm showing you how to draw them out using arrows.
All right, students, so referring back to these problems, I have included the answers within the slide that I have uploaded on Blackboard now. So if you want the answer to the question, pause this video because I'm about to show it. So these are the answers for these specific reactions. Like I said, they're included within the PowerPoint as well. Now we have concluded our discussion on hydrogen nucleophiles. So the next video will continue with oxygen nucleophiles.